Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into black holes, the birth of the universe, and the long winding story that somehow led to a small, quiet world like ours. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the universe together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. If you were to step outside tonight and look up at the sky, you might feel something surprisingly peaceful. The stars seem still. The darkness feels calm. The universe, at least from where you are, appears almost gentle, but this calm is a kind of illusion. Because beyond that quiet sky, the universe is anything but still. It is a place of immense forces, of collapsing stars and invisible giants, of energy moving in ways that are almost impossible to imagine. Entire suns live and die in bursts of light so powerful they briefly outshine whole galaxies. Regions of space twist and bend under the weight of gravity, and somewhere, at the heart of nearly every galaxy, including our own, there are objects so dense that not even light can escape them. And yet, here you are, sitting or lying down, perhaps wrapped in a blanket, breathing slowly, on a planet where oceans rise and fall gently, where the air is just right, where life has found a way not only to exist, but to wonder. There is something quietly remarkable about that contrast. A violent universe giving rise to a calm world. And so, as we begin, there is a simple question that will guide us. Like a soft thread woven through everything that follows. How does something so chaotic create something so stable? To begin answering that, we have to go back. Not just thousands of years, not even millions, but billions. Back to a time before stars, before planets, before anything that could shine or reflect light. A time when the universe itself was just beginning to unfold. You might have heard this moment described as the Big Bang. It's often imagined as a kind of explosion, like a firework bursting outward into empty space. But that image, while dramatic, isn't quite right. It wasn't an explosion in space, it was the expansion of space. Imagine for a moment a vast, soft fabric. On this fabric are tiny dots, representing everything that exists: matter, energy, the seeds of future stars. Now imagine that fabric stretching, slowly and steadily. The dots aren't flying through space away from a central point. Instead, the space between them is growing. Everything moves apart, because space itself is expanding. In those earliest moments, the universe was incredibly hot, incredibly dense, not filled with stars or galaxies, but with something far simpler. Tiny particles, energy, the most basic ingredients of reality. As the universe expanded, it cooled. And in that cooling, something subtle began to happen. The simplest elements formed. Hydrogen, the lightest of all elements, and helium, just a little heavier. These would become the raw materials of everything to come. But at this stage, the universe was still dark. There were no stars yet, no glowing points in the sky, just vast clouds of invisible gas, slowly drifting, slowly spreading, carried along by the expansion of space. And if you could have been there, floating in that early universe, you wouldn't have seen anything at all. No light, no colour, just a quiet, endless darkness. It's a strange thought, isn't it? That before there was light, There was simply time and space and the faint beginning of structure. But even in that darkness, something was already at work, a force so familiar that we barely think about it, and yet so powerful that it shapes the entire universe. Gravity. You can think of gravity not as something pulling objects together through empty space, but as the way space itself curves and bends. Massive things, like clouds of gas, create gentle dips in the fabric of space, and other things naturally drift into those dips, like leaves sliding toward the center of a quiet pond. At first, these effects were small, almost imperceptible, but over millions of years and then hundreds of millions, gravity began to gather matter together. Clouds of hydrogen slowly grew denser. Regions of space that were once almost uniform began to develop subtle differences, slightly thicker here, slightly thinner there, and those small differences became the seeds of everything that followed. It's a bit like watching mist gather in the early morning. At first, it's evenly spread, barely noticeable, but given time, it begins to collect, forming shapes, patterns, gentle swirls that weren't there before. In the universe, those swirls would eventually become stars, but not yet. For a long time, there was only darkness, and the slow, patient pull of gravity shaping the future in silence. And perhaps there is something comforting in that idea, that even in complete darkness, even in the absence of structure or light, there can still be a quiet kind of progress, a gradual unfolding, a movement towards something more complex, more luminous, more alive. The universe did not rush. It did not burst instantly into the form we recognize today. Instead, it took its time. Hundreds of millions of years passed before the first star began to ignite, before the universe lit up for the first time, and when that light finally came, it would change everything. Because those first stars would begin a cycle, a slow, repeating rhythm of birth and death, that would eventually create the elements needed for planets, for oceans, for life itself, even for you. But for now, we remain in that quiet early chapter. The universe still dark, still forming, still preparing, a calm before a very long and very gentle kind of storm. And as we let that image settle, like distant fog across an endless landscape, we can begin to drift a little deeper into the story, toward the moment when the first lights appeared and the universe at last began to glow. If you stay with that image for just a moment longer, a universe that begins not with a bang echoing through empty space, but with space itself quietly stretching, something interesting begins to shift in how it feels. It becomes less like a sudden event and more like a slow opening, like a breath being taken in. When scientists describe the beginning of the universe, they often speak in terms of temperature, density, and energy. But behind those technical words is something almost gentle. The universe did not explode outward into something that was already there. There was no empty stage waiting for it. The stage itself was being created, space was expanding, and with it time began to flow. If you imagine a balloon, not as a solid object but as a flexible surface, and you place tiny dots on it, then slowly inflate it, you'll notice something subtle. Each dot moves away from every other dot, not because the dots are moving on their own, but because the surface itself is stretching. From any one dot's perspective, it looks as though everything else is drifting away, and this is very close to what we observe when we look out into the universe today. Galaxies, vast collections of stars, are moving away from each other. The farther they are, the faster they seem to recede. This observation was first carefully described by the astronomer Edwin Hubble, and it gave us one of the clearest clues that the universe is still expanding even now. But if we gently rewind this process, if we imagine that expansion playing backward like a film in reverse, everything comes closer together. Galaxies drift inward, distances shrink, temperatures rise, until eventually everything is compressed into a state so dense, so hot, that it becomes difficult to describe in ordinary terms, not a point in space, but a condition of space itself. At that earliest moment, the universe was filled with energy in a very raw form, not atoms, not even protons or neutrons as we know them, just a kind of energetic soup, constantly shifting, constantly interacting. As the universe expanded and cooled, these energies began to settle into more stable forms, particles formed. Then, as time moved forward, though at that stage time itself behaved in ways we're still trying to understand, those particles began to combine. Protons and neutrons came together to form the nuclei of atoms, and over time these nuclei captured electrons, forming the first true atoms, mostly hydrogen and some helium. If you think of hydrogen as a single, simple note, then helium is a slightly richer tone, and together they formed the earliest music of the universe. There were no complex molecules yet, no carbon chains, no oxygen to form water. Just these two basic elements, spread out across an ever-expanding cosmos. And yet, within this simplicity, everything that would ever exist was already quietly encoded. It's a little like planting a seed. At first it looks almost empty, just a small, unassuming form, but inside it is the potential for roots, for leaves, for an entire tree. The early universe was like that seed. Now, as space continued to expand, something else began to happen, something that would eventually allow light to travel freely. In the very early moments, the universe was so hot and dense that light could not move far without being scattered. It was like trying to shine a flashlight through thick fog. The light would bounce around, never travelling in a straight line. But as the universe cooled, it reached a point where atoms could form stably. Electrons settled into orbits around nuclei, and suddenly, light could move more freely. This moment is sometimes described as the universe becoming transparent, and the light released at that time, though stretched and softened by billions of years of expansion, still exists today. It fills the universe as a faint glow, like a distant echo of its earliest moments. You can think of it as a kind of afterglow, a memory of when the universe first allowed light to travel unimpeded. But even with light now free to move, there were still no stars. The universe at this stage was vast, dim and quietly structured. Clouds of hydrogen and helium drifted through space guided by gravity, but not yet igniting into the brilliant objects we now see in the night sky. This period is often called the Cosmic Dark Ages, and despite the name, it wasn't a time of chaos or confusion. It was a time of patience. Gravity continued its quiet work, gently pulling matter together. Slight variations in density, tiny differences left over from the earliest moments, began to grow. Regions that were just a little denser attracted more matter, and as they grew, their gravitational pull became stronger, drawing in even more material. It's a slow process, but a powerful one, like snow gathering on a hillside. At first, each flake lands softly, barely noticeable. But over time, the accumulation becomes significant. A small drift becomes a mound, and the mound begins to shape the landscape. In the universe, these growing regions of matter would eventually become the cradles of the first stars, but we're not quite there yet. At this point in our journey, the universe is still in a kind of quiet preparation. The ingredients are in place, the conditions are forming. But the transformation has not yet begun, and there's something deeply soothing about that idea, that before the brilliance, there was stillness. Before the light, there was a long, quiet unfolding, and perhaps in some small way, it mirrors the way things happen in our own lives. The most visible moments the bright dramatic ones, often come after long periods of quiet change that we barely notice at the time. The universe, it seems, works in much the same way. Nothing is rushed, everything unfolds, and as gravity continues to gather matter, shaping the first dense regions in this vast expanding space, we begin to approach a turning point, a moment when the darkness will finally give way and the first stars will begin to shine. If you imagine yourself drifting gently through that early universe, there is something almost peaceful about it. No stars overhead, no constellations to trace, no bright points of light to guide your sense of direction. Just a vast, quiet darkness stretching in every direction like an endless night without a horizon. And yet, this darkness was not empty. It was filled with possibility. Clouds of hydrogen and helium, spread across unimaginable distances, were slowly moving, slowly shifting, drawn together by the quiet persistence of gravity. There were no sudden movements, no sharp edges, no dramatic events, just a gradual gathering, like breath condensing on a cold window, forming patterns so subtle you might miss them if you weren't looking closely. This era, often called the Cosmic Dark Ages, lasted for hundreds of millions of years. And while that might sound like an impossibly long time, in the life of the universe, it was simply part of a larger rhythm. A pause, a preparation. Gravity, as we've come to understand, is not a force that pushes or pulls in the usual sense. It is the way mass shapes the space around it. And even the smallest unevenness, tiny differences in how matter was distributed, was enough to begin this slow process of gathering. Some regions of space were just slightly denser than others, and that was enough. Because once a region becomes a little denser, it pulls in more matter, and as it gathers more matter, its influence grows. It becomes a kind of quiet center, drawing in gas from its surroundings. It's a little like watching a drop of ink fall into still water. At first it barely changes anything, but slowly, gently, the ink begins to spread, to swirl, to create patterns that weren't there before, and over time, those patterns become more defined, more complex. In the early universe, those patterns were the beginnings of structure. Over vast stretches of time, matter gathered into long, delicate strands, forming something like a cosmic web. Enormous filaments of gas stretched across space, intersecting at dense knots where more and more material collected. Between these filaments were vast empty regions, voids so large that even galaxies would one day seem sparse within them. But at this stage, there were still no galaxies, only the scaffolding, only the faint outlines of what would eventually become the large-scale structure of the universe. If you could see it, not with your eyes, but with some deeper sense, you might notice that the universe was beginning to organize itself, not through intention, not through design, but through simple rules playing out over immense stretches of time. And within the densest regions of this growing structure, something important was beginning to happen. As clouds of gas gathered, they became thicker, heavier, more compressed. And as they compressed, their internal conditions began to change. Pressure increased, temperature rose. At first, these changes were subtle, but as more and more matter fell inward, the process accelerated. The center of each cloud became hotter and denser, while the outer regions continued to drift inward. You can imagine it like a slow inward spiral, or like pulling a soft blanket tighter and tighter toward a single point. Eventually, in the densest parts of these clouds, the temperature rose high enough for something remarkable to occur. The atoms themselves began to interact in a new way. Hydrogen nuclei, simple single protons, were pushed so close together that they could combine, forming helium. And in that process, a small amount of mass was converted into energy, not in a violent flash, but in a steady release, a gentle ignition. This was nuclear fusion, the a process that would power every star that would ever shine. And with that first ignition, the darkness began to lift. The very first stars were born. They were not like the stars we see today. These early stars were enormous, many times more massive than our sun. They burned hotter, brighter, and lived much shorter lives. Where our sun might shine for billions of years, these first stars live for only a few million. Brilliant and brief. But their importance cannot be overstated. Because before they existed, the universe was made almost entirely of hydrogen and helium. Simple elements, light elements. But inside these first stars, something new began. As fusion continued, helium was transformed into heavier elements. And in the final stages of these stars' lives, even more complex elements were created. Carbon, oxygen, and beyond. Elements that would one day become the building blocks of planets, of water, of living things, of you. It's a quiet realization, but a profound one, that the atoms in your body were not created all at once at the beginning of the universe. They were forged, slowly, inside stars that lived and died long before our sun was even born. The first stars were like the universe's first experiments in complexity. And when they reached the end of their lives, they did not simply fade away. They ended in events that, while powerful, were also part of a larger cycle. Their outer layers were cast back into space, carrying with them the elements they had created. And those elements mixed with the surrounding gas, enriching it, preparing it for the next generation of stars. A cycle had begun. Birth, transformation, release, and renewal. And as more stars formed and more generations lived and died, the universe gradually became richer, more complex, more capable of forming the kinds of structures we recognize today. Galaxies would begin to take shape. Planets would eventually form. And in some quiet corner of one of those galaxies, conditions would align just right for life to emerge. But all of that lies ahead. For now, we remain close to that first moment of light. A universe that had known only darkness for so long, now beginning to glow. And if you imagine that glow, not as something sudden or overwhelming, but as a gentle spreading of light across an endless expanse, it begins to feel less like an explosion and more like a sunrise. A very slow sunrise, one that took millions of years to fully unfold. And in that first light, the universe took its next step, from simplicity toward complexity, from darkness toward structure, from stillness toward motion, from quiet beginnings toward everything that would follow. As that first gentle light spreads across the universe, something begins to change in the rhythm of everything. What was once quiet and evenly dark now becomes textured. Pockets of brightness appear, scattered across the vastness like the first distant lanterns in an endless night. These are the earliest stars, enormous, luminous, and unlike anything we see in the sky today. If you imagine standing beneath them, they would not feel familiar. They would feel overwhelming. Not because they were violent in a chaotic sense, but because of their sheer scale. These first stars were immense, many times more massive than our sun. And with that size came a kind of intensity that shaped everything about their existence. They burned hotter, brighter, and far more quickly than the stars we know today. It's a little like comparing a slow-burning candle to a roaring furnace. A candle can last for hours, gently releasing its energy. A furnace, on the other hand, consumes its fuel rapidly, pouring out heat and light in a much shorter time. The first stars were like those furnaces, and inside them, something extraordinary was happening. At their cores, under immense pressure and temperature, the simplest atoms in the universe, hydrogen, were being transformed. When hydrogen atoms are pushed close enough together, they can merge, forming helium. In that process, a small amount of their mass is converted into energy. You can think of it as a kind of exchange, a tiny bit of matter becoming light. This is the process that powers all stars, even our sun. But in these early stars, it happened at a much faster and more intense rate. The higher the mass of a star, the stronger the pressure in its core, and the more rapidly it burns through its fuel. And so, while our sun has a lifespan measured in billions of years, these first stars lived only a few million, a brief existence on a cosmic scale. But within that brief existence, they changed the universe forever. As fusion continued in their cores, helium itself began to fuse into heavier elements. And as the temperatures rose even higher, more complex elements formed: carbon, oxygen, and others that would one day become essential for planets and life. It's a quiet transformation, but a profound one. Because before these stars, the universe was simple. After them, it would never be simple again. You might imagine these stars as the universe's first great experiments in complexity. They took the simplest ingredients, hydrogen and helium, and through pressure and heat began to create something richer, something more structured, something more interesting. And yet, despite their brilliance, these stars carried within them the seeds of their own endings. Because as they fused lighter elements into heavier ones, they were gradually building up material that could no longer release energy in the same way. At a certain point, the process that had sustained them began to falter. The balance between outward pressure, created by energy, and inward pull, caused by gravity, began to shift. For most of a star's life, these two forces exist in a kind of quiet equilibrium. Gravity tries to pull everything inward. Energy from fusion pushes outward, and the star remains stable. But when the fuel begins to run out, that balance can no longer hold. Gravity, patient and persistent, begins to take over. The core of the star starts to collapse inward. Layers of material fall toward the center, accelerating as they go. And in the final moments, this collapse can trigger one of the most powerful events in the universe, a supernova. It's often described as an explosion, and in some ways it is. But rather than thinking of it as something sudden and chaotic, you might imagine it as a kind of release, a star that can no longer support itself, giving way, and in doing so, sending its outer layers outward into space. The light from such an event can briefly outshine an entire galaxy. But even here, in what seems like destruction, there is a deeper kind of creation. Because during this final collapse and release, the conditions become extreme enough to form even heavier elements: iron, gold, and many others, elements that cannot be created during the quieter phases of a star's life. And these elements are not lost, they are scattered. Carried outward by the expanding cloud of material, they mix with the surrounding gas. Over time, they become part of new clouds, new stars, and eventually, new worlds. It's a cycle, a slow repeating rhythm that unfolds across billions of years. Stars are born from clouds of gas. They shine, transform, and create new elements. And when they reach the end of their lives, they return those elements to the universe, enriching it, preparing it for the next generation. If you pause for a moment and follow that chain of events, it leads somewhere quite personal. The carbon in your body, the oxygen you breathe, the calcium in your bones. All of these elements were formed inside stars. Not in the stars we see today, but in stars that lived and died long before our solar system existed. You are, quite literally, made of material that has passed through this cycle. Matter that has been part of multiple stars, multiple transformations, multiple beginnings and endings, and there is something quietly beautiful in that. That the same processes shaping distant galaxies also shaped you. That the universe is not separate from you, but continuous with you. As these early stars lived out their short, brilliant lives, more and more of the universe became enriched with heavier elements. The simple clouds of hydrogen and helium began to change, becoming more complex, more capable of forming new kinds of structures. And with each generation of stars, the universe moved a little closer to something familiar. Galaxies began to take shape. Clusters of stars formed, bound together by gravity. And in the densest regions, something even more unusual began to emerge. Some stars, at the end of their lives, did not simply scatter their material and fade. Instead, their cores collapsed so completely, so intensely, that they formed something entirely new, something that would challenge our understanding of space, time, and even light itself, something we now call a black hole. And as we gently follow the story forward, from these first stars to the strange objects they leave behind, we begin to step into one of the most mysterious parts of the universe, a place where gravity becomes so strong that even light cannot escape. As the story of those early stars unfolds, something begins to shift in tone. Until now, we've been following a rhythm that feels almost gentle. Clouds gathering, stars igniting, light slowly spreading through the darkness. Even the deaths of stars, though powerful, have carried a sense of renewal, an ending that leads to something new. But not all endings are the same. Some stars reach a point where the transformation goes further, deeper, into something far more unusual. To understand this, it helps to return to that quiet balance we mentioned earlier. A star lives its life in a delicate equilibrium between two opposing tendencies. On one side, gravity is always pulling inward, trying to compress the star. On the other side, energy produced in the core pushes outward, holding everything up. As long as these two influences are in balance, the star remains stable. But when the fuel in the core begins to run out, that balance starts to falter. For smaller stars like our Sun, the ending is relatively gentle. They shed their outer layers, forming glowing shells of gas, and leave behind a dense core called a white dwarf, a quiet remnant that slowly cools over time. But for much larger stars, the story takes a different turn. When a massive star exhausts its fuel, the pressure from fusion drops suddenly. Gravity, which has been patiently waiting, takes over. The core collapses inward with tremendous force, compressing matter to extraordinary densities. What happens next depends on just how massive that core is. In some cases, the collapse is halted at a certain point. The core becomes so dense that it resists further compression, forming what we call a neutron star. To picture this, imagine taking something as large as the Earth and compressing it down to the size of a small city. Matter becomes so tightly packed that the usual structure of atoms breaks down. Electrons and protons merge into neutrons, forming an object that is incredibly dense yet still finite. Some of these neutron stars spin rapidly, emitting beams of radiation that sweep across space like lighthouse beams. When those beams pass by Earth, we detect them as regular pulses, which is why they are often called pulsars. There is something almost rhythmic about them, a steady ticking in the vastness of space. But if the original star is even more massive, the collapse does not stop there. Gravity continues to compress the core, pushing it beyond the limits of what matter can resist. And at that point, something remarkable happens. The core collapses into what we describe as a black hole. It is not a hole in the usual sense. It is not an empty space. Instead, it is a region where matter has been compressed to such an extent that it profoundly alters the surrounding space itself. You might imagine space as a flexible surface. When a massive object is placed on it, the surface dips slightly. This is the gentle curvature we associate with gravity. But in the case of a black hole, that curvature becomes extreme. the dip becomes more like a deep well, a steep descent from which there is no easy return. At a certain boundary around this region, something very important occurs. This boundary is often called the event horizon. Rather than thinking of it as a physical surface, you can think of it as a threshold, a point beyond which escape is no longer possible, not because something is physically blocking the way, but because the structure of space itself is so curved that all possible paths lead inward. Even light, which normally travels faster than anything else we know, cannot find a path back out once it crosses this boundary, and that is why black holes appear black. They do not emit light from within, they do not reflect it, they simply absorb anything that crosses that threshold. But despite this, black holes are not entirely invisible. In fact, some of the most energetic and luminous phenomena in the universe occur just outside them. As gas and dust fall toward a black hole, they do not simply disappear all at once. Instead, they spiral inward, forming what is known as an accretion disk, a swirling structure of material that heats up as it compresses and accelerates. You can think of it like water spiraling down a drain, but on a vastly larger scale and with much greater energy. As this material spirals inward, it heats up to extraordinary temperatures, emitting light across many forms, from visible light to higher energy radiation. In some cases, powerful streams of particles are launched outward along the black hole's poles, travelling at speeds close to that of light. So while the black hole itself remains hidden, its presence is revealed by the behaviour of everything around it. We detect it not directly, but through its influence, and there is something quietly fascinating about that one of the most mysterious objects in the universe is known not by what it shows, but by what it does. Now, it's easy to imagine black holes as purely destructive, as cosmic endpoints where everything is lost, but the reality is more nuanced. Black holes are part of the same cycle that we've been following all along. They are born from the deaths of massive stars, and in turn they influence the structure of galaxies, the movement of matter, and the distribution of energy across vast distances. In that sense, they are not just endings, they are transitions, and perhaps that is one of the quiet themes that runs through the entire universe, that what appears to be an end is often part of a larger process, a transformation rather than a conclusion. As more stars lived and died, more black holes formed. Some remained relatively small, scattered throughout galaxies. Others, over time, would grow, merging with other black holes, gathering matter, becoming something far larger. And at the centres of galaxies, including our own Milky Way, these processes would give rise to objects of truly immense scale. Black holes so massive that they shape the galaxies around them. But that is a story we will ease into slowly. For now, we remain close to this moment, where the life of a star leads not only to light and elements, but to something deeper, a place where gravity becomes so strong that it reshapes space itself. And as we continue, we'll begin to explore these strange objects more closely, not as distant monsters, but as quiet, powerful participants in the unfolding story of the universe. If we gently pause here, at the moment when a star reaches the end of its life, there is something worth noticing. From a distance, a supernova might seem like the most violent kind of ending imaginable, a star collapsing, then releasing an immense burst of light and energy, sending its outer layers rushing outward into space. It sounds dramatic, almost chaotic. But if you look a little more closely, there is a quiet kind of purpose hidden within that moment, because these explosions are not just endings. They are a kind of distribution, a way for the universe to take what was once concentrated in a single place and gently spread it outward across vast distances. Inside a star, elements are built step by step, hydrogen becomes helium. Helium becomes heavier elements, and as the star ages, it begins to create more complex forms of matter: carbon, oxygen, silicon, iron. You might think of it like layers forming inside a slowly cooking dish. Each stage adds something new, something richer, something more complex than what came before. But all of those elements are locked inside the star until the very end. And when that end comes, the star does something remarkable. It lets go. The outer layers are cast outward, expanding into space, carrying with them all the elements that were formed deep within the core. What was once hidden becomes part of the wider universe. And over time, those elements drift, mix, and gather again. If you could watch this process unfold, not over seconds or minutes, but over millions of years, you would see something almost like a slow-moving cloud, expanding and fading, its contents gradually blending into the surrounding space. It is not a sudden dispersal. It is more like a gentle release. And this release has consequences that stretch far beyond the moment itself. Because once those heavier elements exist outside the star, they become available for something new. New stars, new systems, new possibilities. The universe, which began with only the simplest ingredients, begins to change in character. It becomes more complex, more varied, more capable of forming structures that were not possible before. And eventually, in some quiet corner of space, these enriched clouds begin to gather again. Gravity draws them inward, just as it did before. But this time, the material is different. It is no longer just hydrogen and helium. It carries traces of earlier stars, carbon, oxygen, iron, and other elements that will play crucial roles in what comes next. And from these enriched clouds, a new generation of stars begins to form. Stars that are not quite like the first ones. Stars that are part of a continuing story. Now, if we follow this chain of events just a little further, something interesting begins to emerge. Those heavier elements, the ones formed in the hearts of stars, are not only important for building more stars, they're essential for building planets. Without elements like carbon and oxygen, there would be no complex molecules, no water, no solid surfaces where chemistry could unfold in more intricate ways. In a very real sense, planets are made possible by the lives and deaths of earlier stars, and if we continue that line of thought, it leads somewhere even more personal. The carbon in your body, the atoms that form the structure of every cell, were created in the cores of stars. The oxygen you breathe was once part of a star's internal processes. Even the iron in your blood, which allows oxygen to be carried through your body, was forged under extreme conditions during the final moments of a star's life. It is a quiet connection, but a profound one. You are not separate from this story. You are part of it. Your body is made of elements that have travelled across space, passed through multiple cycles of formation and release, and eventually became part of a world where life could take hold. And yet, none of this required intention. No plan, no design in the way we might usually think of it. Just simple processes, repeated over immense stretches of time. Stars forming, evolving, and releasing their contents. Matter cycling through different states, becoming more complex with each generation. And slowly, almost imperceptibly, the universe becoming a place where something like life could exist. There is something quietly reassuring in that idea, that complexity does not have to appear all at once. It can emerge gradually, from simple beginnings, through repeated cycles, guided by consistent rules. Even something as dramatic as a supernova fits into that pattern, not as a disruption, but as a necessary step, a way for the universe to move forward. If we zoom out just a little and imagine many stars going through this process across a galaxy, the effect becomes even more significant. Each star contributes its own share of elements. Each explosion adds to the collective pool. Over time, entire regions of space become enriched, filled with the materials needed for more complex structures. Galaxies begin to take on distinct shapes. Clouds of gas and dust swirl and settle into patterns, and within these patterns new stars are born, surrounded by disks of material that may one day become planets. It is a slow transformation, but a steady one. And throughout it all there is a kind of quiet continuity. Nothing is wasted. Everything is reused. Matter is not lost. It is simply rearranged. And as these processes continue, something else begins to happen. In the densest regions of galaxies, where stars are more tightly packed and interactions are more frequent, the remnants of these stellar lives begin to accumulate. Black holes, formed from the collapse of massive stars, start to play a larger role. They grow, they merge, they influence the motion of surrounding matter, and over time, some of them become so large that they sit at the centers of galaxies, quietly shaping everything around them. But even here, the story does not become chaotic. It remains structured, guided by the same simple principles that have been present from the beginning: gravity, energy, time, and the gradual unfolding of complexity. So when we think about these explosions, the supernovas that mark the end of a star's life, it may help to see them not as isolated events, but as part of a larger rhythm, a cycle that connects the smallest particles to the larger structures. A process that takes something simple and step by step transforms it into something more intricate. And somewhere along that path, it leads to a quiet planet, an atmosphere, an ocean, a place where, for a brief moment in cosmic time, the universe becomes aware of itself. As we move gently from the lives of stars and the quiet remains they leave behind, there is a subtle shift in perspective waiting for us. Up to now, we've been describing gravity in a very familiar way, as something that pulls, something that draws matter inward, something that gathers clouds, forms stars, and eventually shapes entire galaxies. And in everyday life, that description works perfectly well. When you drop an object, it falls. When the moon circles the Earth, it follows a path that seems guided by an invisible pull. Gravity feels like a force, simple, direct, and easy to imagine. But as we begin to look more closely, especially at extreme places like black holes, that simple picture starts to feel incomplete. To understand what is really happening, we need to take a small step deeper, not into something more complicated, but into something more subtle. In the early 20th century, a physicist named Albert Einstein began to rethink gravity in a completely different way. Instead of asking, what force is pulling objects together, he asked a quieter question. What if nothing is being pulled at all? What if objects are simply following the natural shape of the space they're in? It's an idea that can feel unusual at first, but with the right image, it becomes almost intuitive. Imagine a large, soft surface, like a stretched piece of fabric. If you place a small object on it, the surface barely changes. But if you place something heavy in the center, a bowling ball for example, the fabric dips. Now, if you roll a smaller ball across that surface, it doesn't move in a straight line anymore. It curves inward, following the shape created by the heavier object. From a distance, it might look as though the smaller ball is being pulled toward the center, but in reality, it's simply moving along the curved surface. Nothing is reaching out to grab it. It is just following the path that the surface allows. In Einstein's view, this is what gravity really is. Not a force pulling objects through space, but the shape of space itself guiding how things move. And not just space alone, but space and time together, woven into a single structure that gently curves in the presence of mass. You don't need to picture this as something rigid or mechanical. It's more like a flexible landscape, one that changes depending on what is within it. A star creates a gentle slope, a planet creates a smaller one, and something like a black hole creates a deep and dramatic curve. Objects moving through this landscape simply follow its contours. They take the paths that are available to them, and those paths, which might look curved or circular to us, are actually the most natural routes in a curved space. It's a little like walking across a hilly landscape. If the ground beneath you slopes downward, you naturally follow that slope. You don't feel like you're being pulled, you just move along the easiest path. Gravity, in this sense, is not something acting on you from the outside. It is the shape of the path you're already on. Now, this idea becomes especially important when we think about light. Light does not have mass in the way objects do, and yet it is still affected by gravity. If light passes near a massive object, like a star or a galaxy, its path bends. Not because something is pulling on the light, but because the space through which it travels is curved. This effect has been observed many times. Light from distant galaxies can be bent around massive objects, creating arcs and rings of light like reflections seen through a curved piece of glass. It's a quiet but powerful confirmation of this idea, that space itself can be shaped, and that everything within it, matter, energy, even light, moves according to that shape. As we approach black holes, this picture becomes even more striking. The curvature of space becomes so extreme that the paths available to objects begin to change dramatically. Imagine standing near a deep valley. At first, the slope is gentle. You can walk in any direction, and with enough effort you can move away from the centre. But as you move closest to the deepest part, the slope becomes steeper. At some point, no matter which direction you try to go, the ground beneath you leads downward. All paths point inward. This is similar to what happens near a black hole. The curvature of space becomes so intense that beyond a certain boundary, every possible path leads deeper inside. There is no direction that leads outward anymore, and this boundary is what we call the event horizon. But it's important to remember, this is not a surface you can touch. It is not a wall or a barrier. It is simply the point where the shape of space changes in such a way that escape is no longer possible. From the outside, it appears as though something has been captured, but from the perspective of space itself, the object is simply continuing along its path, following the curve. There is something almost calming in that idea, that even in the most extreme environments, nothing is being forced or pushed in a violent way. Everything is simply moving as it must, according to the structure of the space around it. And this perspective begins to change how we think about black holes. They are no longer just places where things disappear. They are regions where the geometry of the universe becomes so pronounced, so deeply curved, that it reveals something fundamental about reality itself. That space is not fixed, that it can bend, stretch, and change, and that everything within it is part of that quiet, continuous motion. As we continue, we'll move a little closer to that boundary, to the place where light itself can no longer find a path back, not as a sudden fall, but as a gentle crossing into a region where the rules feel different, where the familiar sense of direction begins to soften, and where the universe reveals one of its most mysterious transitions. As we linger with this idea of space gently curving, it becomes easier to approach something that once felt almost impossible to imagine, a boundary where even light cannot return. Not a wall, not a surface you could touch, but a subtle threshold in the structure of space itself. If you picture that curved landscape again, the one shaped by mass, then near a black hole, that landscape becomes increasingly steep. At first, the slope is gentle, like a shallow valley, You could wander across it, change direction, even climb your way back out. But as you move closer to the center, the slope deepens. Paths that once felt open begin to narrow. Directions that once led outward begin to curve back inward. The freedom to choose where you go becomes more limited, not because anything is stopping you, but because the shape of space itself is guiding you. There comes a point where this change becomes complete, a place where every possible path leads inward. This is what we call the event horizon, but instead of imagining it as a barrier, it may help to think of it as a point of no return in a flowing landscape, a gentle but irreversible crossing. A useful way to picture this is with a river. Imagine standing at the edge of a wide, slow-moving river. At first the water moves gently. You could swim against it if you wanted to, or simply float and drift along. There is freedom in how you move. As you follow the river downstream, the current becomes stronger. Swimming upstream requires more effort. You can still do it, but it becomes increasingly difficult. Further ahead, the river narrows and the water begins to move more quickly. You can feel the pull becoming stronger, more insistent. At some point, even your strongest effort might not be enough to move against it. And then, somewhere ahead, there is a waterfall. Before you reach it, there is a final point, a place where the current becomes so strong that no matter how hard you try, you can no longer turn back. That point is like the event horizon. It is not the waterfall itself. It is the moment when turning around is no longer possible, and once you pass it, the journey continues, but only in one direction, toward the center, toward what lies deeper within. Now, from far away, this boundary is invisible. There is no line drawn in space, no sudden change in appearance. If you were watching someone approach a black hole from a great distance, you might not notice anything unusual at first. They would seem to move normally, slowly getting closer. But something subtle would begin to happen. As they approached the event horizon, time itself would appear to slow down. Not for them, but from your perspective as an observer. Their movements would seem to stretch out, becoming slower and slower, as though they were moving through something thick and resistant. The light they emit would become dimmer, shifting toward longer wavelengths, fading gradually into darkness. It would never look like they actually crossed the boundary. Instead, they would seem to linger there, slowing, fading, and eventually disappearing from view. This effect comes from the way gravity influences time. In regions where gravity is stronger, time passes more slowly relative to regions where gravity is weaker. Near a black hole, this effect becomes very pronounced. You don't need to think of it in terms of equations or precise measurements. It's enough to imagine that time itself flows differently depending on where you are, like a river that moves more slowly in some places and more quickly in others. Near the event horizon, that flow becomes extremely slow. But for the person falling in, the experience would feel very different. They would not feel time slowing down. Their own sense of time would remain normal. They would continue moving inward, crossing the event horizon without any sudden jolt or barrier. From their perspective, nothing special marks the crossing. It is only from the outside that the difference becomes apparent, and this contrast between what is experienced locally and what is observed from afar is one of the most intriguing aspects of black holes. Two perspectives, both valid, yet very different. As they move further inward, the curvature of space becomes even more extreme. Pairs that once curved gently now bend sharply. Directions lose their familiar meaning. The idea of outward becomes less and less relevant until eventually all directions lead inward toward the center, toward what is often described as the singularity, a region where matter is compressed to an extraordinary degree. We do not yet fully understand what happens there. Our current theories describe it as a place where the known laws of physics reach their limits, where the concepts we rely on, space, time, matter, begin to behave in ways that are difficult to describe. But rather than focusing on that unknown centre, it can be more comforting to stay with what we do understand, that the journey inward is not chaotic, it is guided, shaped by the same gentle principle we've been following all along, the curvature of space. Even here, in one of the most extreme environments in the universe, there is no sudden violence in the way things move, only a steady continuation, a path that becomes more and more focused, more and more directed as it approaches the centre. And while this might sound unsettling at first, there is also something strangely calming about it, that even in the presence of such immense gravity, the universe does not break into disorder. It remains consistent, predictable in its own way, governed by the same quiet rules that shape everything else. Black holes, then, are not places where the universe becomes chaotic. They are places where its structure becomes most clearly visible, where the geometry of space reveals itself in its most extreme form. And as we step back from this edge, this boundary where light itself cannot return, we begin to notice something else, that black holes are rarely alone. They exist within larger systems, within galaxies, surrounded by stars, gas and dust that continue to move, evolve and interact. And in those larger contexts, black holes play roles that are not only mysterious, but unexpectedly constructive. Roles that influence the growth of galaxies, the movement of matter, and perhaps even the conditions that make life possible. So as we move forward, we'll shift our view once again from the edge of a single black hole to the vast structures that surround them, to the centres of galaxies, where these quiet, invisible objects shape the cosmos on the larger scales. If we gently step back from the edge of that invisible boundary, from the place where light itself can no longer return, something curious begins to appear, because even though black holes do not emit light, they're often surrounded by some of the brightest regions in the universe. It's a quiet paradox, something completely dark, outlined by brilliance. And it is through this contrast that we have come to understand their presence. You see, a black hole on its own is almost impossible to detect directly. It does not glow, it does not reflect, it does not reveal itself in any obvious way. But the universe rarely leaves things in complete isolation. Around black holes, there is often gas, dust, sometimes even entire stars drifting too close. And as this material approaches, it does not simply fall straight in. Instead, it begins to spiral. If you imagine leaves caught in a gentle whirlpool, circling as they move inward, you begin to get a sense of this motion. But unlike water in a basin, the motion here happens across vast distances and under extreme conditions. As the material spirals inward, it forms a thin, flattened structure known as an accretion disk. You don't need to think of it as a rigid disk. It is more like a flowing, luminous ring, a continuous movement of matter circling closer and closer to the centre. And as it does so, something important happens: friction. The particles within the disk move at different speeds. They rub against each other, compress, and heat up. And as the temperature rises, the disk begins to glow. At first, softly, then more intensely. In some cases, the temperatures become so high that the disk shines not only in visible light, but in forms of energy that are far more energetic, forms that we cannot see with our eyes, but can detect with instruments. You might think of it like metal being heated in a fire. At lower temperatures, it glows a dull red. As it becomes hotter, it shifts toward brighter colours, eventually becoming almost white with heat. The accretion disk around a black hole follows a similar progression, though at temperatures far beyond anything we encounter on Earth. And so, even though the black hole itself remains dark, the material around it becomes brilliantly visible. It is as if the darkness reveals itself by the way it transforms its surroundings. Now, in some cases, this process becomes even more dramatic. Not all of the material spiraling inward ends up crossing the event horizon. Some of it is redirected, channeled along the rotational axis of the black hole, and expelled outward in narrow streams. These streams, often called jets, extend far into space, carrying energy and particles across enormous distances. If you imagine a spinning top, with energy flowing along its axis, you begin to get a sense of how these jets are aligned. They are not chaotic bursts, they are focused, structured, and they can stretch across regions larger than entire galaxies. It's a remarkable thought that something so compact, so hidden, can influence space on such a vast scale. But even when these dramatic features are not present, there are quieter ways in which black holes reveal themselves. One of these involves light bending around them. As we discussed earlier, gravity is not just a pull, it is a shaping of space. And when light passes near a massive object, it follows that curved space. This means that light from objects behind a black hole can be bent around it, creating arcs or rings of light that seem to wrap around the darkness. It's a bit like looking through a curved piece of glass. The image behind it becomes distorted, stretched, sometimes even duplicated. In the case of black holes and other massive objects, this effect allows us to see things that would otherwise be hidden, their light redirected along curved paths. In this way, black holes act like lenses, not by design, but as a natural consequence of how they shape space. There are also moments when black holes announce their presence more suddenly. When two black holes drift close enough, they can begin to orbit each other, gradually spiraling inward over time. As they do, they create ripples in the fabric of space itself, subtle waves that travel outward across the universe. These ripples are incredibly faint, but with sensitive instruments we have learned to detect them. They arrive not as light, but as tiny changes in distance, almost like the quiet stretching and compressing of space. You might imagine it as a distant vibration, like the faint sound of a drum carried across a vast landscape. And when these waves reach us, they carry information about the event that created them. A kind of message travelling silently across the cosmos. There are also bursts of energy, brief intense flashes that occur when massive stars collapse or when compact objects interact in extreme ways. These flashes, often in forms of energy beyond visible light, can signal the birth of a black hole or the merging of dense remnants. We don't see the black hole itself, but we see the moment of its creation, a brief illumination, followed by silence, and through all of these observations, glowing disks, bending light, distant ripples, fleeting bursts, we begin to build a picture, not of the black hole directly, but of its influence. It's a bit like standing in a quiet room and noticing a gentle breeze. You don't see the air itself, but you see the curtains move. You feel the shift in temperature. You hear the soft rustle of leaves outside. From these subtle signs, you understand that something invisible is present. Black holes are like that. They reveal themselves through what they change, through the way they shape their surroundings, and as we continue to observe them, we begin to realize that they are not rare exceptions. They are not isolated curiosities scattered randomly across the universe. They are common, found in many galaxies, often at their very centers, quietly influencing the motion of stars, the flow of gas, the growth of entire systems. And as we widen our view from individual black holes to the galaxies that host them, we begin to see a larger pattern emerging, one in which these invisible objects are not just endpoints of stellar evolution, but central players in the ongoing story of the universe. As we widen our view just a little further, beyond individual stars, beyond single black holes, something larger begins to come into focus: galaxies. Vast, slow-turning collections of stars, gas and dust arranged in spirals, ellipses and sometimes more irregular shapes. From a distance they appear calm, almost serene, like luminous islands floating in an endless dark ocean. But at the heart of most of these galaxies, something unexpected resides. A black hole, not a small one formed from the collapse of a single star, but something far more massive. These are called supermassive black holes, and the name, while accurate, only hints at their scale. Some of these objects contain the mass of millions, even billions of suns, all compressed into a region that is, in cosmic terms, surprisingly compact. At the centre of our own galaxy, the Milky Way, there is one such object. It does not shine, it does not call attention to itself, and yet the stars around it move in ways that reveal its presence, tracing orbits that curve tightly, as though circling an invisible anchor. By observing those motions, astronomers have come to understand that something very massive must be there, quietly shaping the paths of everything nearby. And this is not unique to our galaxy. Across the universe, in galaxies of many different shapes and sizes, similar patterns appear. At their centres, stars orbit rapidly around a hidden core, suggesting the presence of these enormous black holes. One of the most striking examples can be found in a distant galaxy known as Messier 87. At its centre lies a black hole so large that it became the first ever to be imaged directly, not by seeing the black hole itself, but by capturing the glowing ring of material around it. That image, faint and softly glowing, revealed a dark centre surrounded by light, a kind of silhouette shaped by gravity itself. It was a quiet confirmation of something long predicted, that these giants truly exist. But beyond their existence, there is a deeper question. What role do they play? At first glance, it might seem that a supermassive black hole would simply consume whatever comes near it, gradually pulling in stars and gas, growing larger over time, and to some extent this does happen. But the reality is more balanced, more subtle. Most of the time these black holes are not actively feeding. They sit quietly at the centres of galaxies, influencing their surroundings through gravity, but not dramatically consuming everything in sight. They are not cosmic vacuums. They are quiet centres. And when they do become active, when gas begins to fall inward and an accretion disk forms, they can have a surprising effect. As material spirals into the black hole, energy is released, not just as light, but sometimes as powerful streams of particles that are launched outward along the poles. These streams can extend far beyond the central region, reaching into the galaxy itself and even beyond. And here is where something interesting begins to happen. Instead of simply drawing matter inward, the black hole begins to influence how matter is distributed outward. The outflows can push gas away from the centre, heating it, stirring it, preventing it from collapsing too quickly into new stars. In this way, the black hole acts not only as a centre of attraction, but as a regulator. It helps control the rate at which stars form within the galaxy. If too much gas gathers too quickly, the black hole's activity can slow things down, dispersing the material, spreading it across larger regions. If too little activity occurs, gas can settle and form new stars more easily. It is not a precise mechanism in the way a machine might operate, but over time it creates a kind of balance, a gentle shaping. You might think of it like a gardener tending to a vast invisible landscape, not planting each seed directly, but influencing how things grow, how they spread, how they evolve. And because of this, galaxies are not just collections of stars, they are systems that grow, change, and regulate themselves over time, and at the centre of many of them is a black hole quietly participating in that process. There is also another layer to this story. As galaxies evolve, they sometimes come close to one another. Their gravitational fields interact, and over long periods of time they can merge, two galaxies slowly blending into one. When this happens, their central black holes can also come together. They begin to orbit each other, gradually drawing closer until eventually they merge as well. This merging process releases energy in a very different form, not light, but ripples in the structure of space itself. Subtle waves that move outward, carrying the signature of the event across vast distances. These mergers contribute to the growth of supermassive black holes, allowing them to become even larger over time, and as they grow, their influence extends further, shaping larger regions of space. So when we look at a galaxy, we're not just seeing stars scattered randomly. We're seeing a structure that has been shaped over billions of years by gravity, by the life cycles of stars, and by the quiet, persistent presence of something at its centre, something invisible, yet deeply influential. And perhaps one of the most surprising aspects of this is how calm it all appears from a distance. A galaxy does not look chaotic, it looks graceful. Spiral arms curving gently, stars orbiting in steady paths, light spreading softly across space, and at the centre of it all, a black hole. Not as destructive force dominating everything, but as a quiet participant in a much larger system, helping to shape it, to guide it, to maintain a kind of balance over time. And as we begin to understand this role, something shifts in how we think about black holes. They are no longer just the endpoints of massive stars. They are not just places where matter disappears. They are part of the architecture of the universe, part of the way structure emerges and evolves. And if we follow that idea just a little further, we begin to see how their influence might extend beyond galaxies, beyond stars, and into the very conditions that allow planets and eventually life to form, not directly, not intentionally, but as part of a long chain of processes that connect the larger scales of the universe to the smallest details of our own existence. As we continue to widen our view, from stars to galaxies, and from galaxies to the quiet giants at their centres, something begins to shift in how we think about black holes. Up to this point, they may have seemed like endpoints, the final stage of a massive star, a place where matter disappears, where light cannot return, where the story, in some sense, comes to an end. But when we look more closely, when we follow the effects they have on their surroundings over long stretches of time, a different picture begins to emerge. Not of endings, but of influence. Not of destruction alone, but of participation. Because black holes, especially the massive ones at the centres of galaxies, do not simply sit in isolation. They interact. Quietly, steadily, and on scales that are easy to overlook if we focus only on the dramatic moments. When matter drifts too close to a black hole, it begins that familiar inward spiral, forming a luminous disk. As this process unfolds, energy is released, not only as light, but also as motion. And in certain conditions, part of that energy is directed outward, not randomly, but in narrow, focused streams. These streams, often called jets, emerge along the rotational axis of the black hole. They move at extraordinary speeds, carrying particles and energy far beyond the central region of the galaxy. If you imagine a fountain where water is pushed upward and outward before falling back down, you begin to get a sense of how these jets extend into space. But unlike a fountain, these streams do not simply fall back. They travel, sometimes across distances larger than the galaxy itself, and as they move, they interact with the surrounding environment. Gas that might otherwise settle quietly into dense clouds is stirred, heated, and sometimes pushed outward. Regions that might have collapsed too quickly into stars are gently disrupted, spread out, redistributed. At first glance, this might seem like interference, a disturbance, but over time, it contributes to something more balanced. Without this influence, galaxies might form stars too rapidly, exhausting their supply of gas early in their histories. With it, the process becomes more gradual, more extended, allowing stars to form over longer periods. In this way, black holes help regulate the rhythm of galaxies, not by controlling them directly, but by shaping the conditions in which they evolve. And within that regulation, something important happens. The material that is stirred and spread outward carries with it the elements forged in earlier generations of stars: carbon, oxygen, nitrogen, iron. These elements are not confined to a single region. They are distributed gently, persistently, across larger volumes of space. It is a bit like stirring a drop of colour into clear water. At first, the colour remains concentrated, but with motion, with time, it spreads, becoming part of the whole. Black holes, through their activity, contribute to this spreading. They help ensure that the ingredients for complexity are not locked away in isolated pockets, but are shared across the galaxy. And this has consequences that unfold slowly, but profoundly. Because for planets to form, for chemistry to become intricate, for life to emerge, the right elements must be present, not just in one place, but in many. The universe began with only the simplest elements: hydrogen, helium, and little else. Everything more complex, everything that allows for structure, for diversity, for life, came later, through the lives of stars and the processes that followed. Black holes, in their quiet way, help distribute those results. They are part of the system that takes what was once local and makes it widespread. Now, it's important to remember that this is not a deliberate process. There is no intention behind it, no guiding purpose in the way we might think of design. It is simply the outcome of consistent physical processes, repeated over vast spans of time. Gravity draws matter inward. Energy is released as matter moves and compresses. Some of that energy is directed outward, and through these interactions, patterns emerge. Balance arises, conditions develop, and within those conditions, new possibilities appear. If we follow this chain just a little further, it leads us to a subtle but powerful idea: that the universe does not create life directly. It creates the conditions in which life can emerge, and those conditions are the result of many interconnected processes: stars forming and evolving, explosions releasing elements, galaxies organizing themselves, black holes shaping the distribution of matter and energy. Each step builds on the one before it. Each process contributes in its own way, and over time, the universe becomes a place where complexity is not only possible, but inevitable in certain regions. It's a quiet kind of inevitability, not something that happens everywhere, but something that can happen when the conditions align. And when they do, something remarkable appears: planets with stable surfaces, atmospheres that can hold heat and protect delicate chemistry, liquid water flowing, circulating, interacting, and eventually, life. From the perspective of a black hole, these outcomes are distant and indirect. It does not create life. It does not shape individual planets. But it participates in the larger system that makes those things possible. It is part of the long chain, a link between the large-scale structure of the universe and the small, intricate systems that emerge within it. And perhaps there is something quietly reassuring in that even the most extreme objects, the ones that seem the most distant from our everyday experience, are connected to the same processes that led to our own existence, not in a direct line, but through a network of relationships, a web of interactions that spans from the largest scales to the smallest. As we begin to follow that web more closely, our focus will shift once again, from galaxies to something smaller, from vast structures to a single system, a cloud of gas and dust, slowly gathering, slowly forming around a young star, a place where the elements created and distributed across the galaxy begin to settle into new shapes, into worlds, into surfaces, into environments where something entirely new can begin. And as we move into that quieter, more familiar scale, we begin to see how this long cosmic story gently leads us home. As we gently shift our attention from the vast structures of galaxies to something smaller, quieter, something closer to home, the scale begins to soften. We are no longer looking at millions of stars at once. We are looking at the beginning of just one. Somewhere within a galaxy, perhaps not so different from our own, a cloud of gas and dust begins to gather. Not suddenly, not dramatically, but slowly, almost imperceptibly, shaped by the same quiet pull of gravity that has guided everything so far. This cloud is cold, diffuse, spread across a wide region of space. But over time, small variations begin to grow. Some parts of the cloud become slightly denser than others, and as they do, they begin to pull in more material, becoming denser still. It's a gentle feedback, a soft gathering, like mist slowly condensing into droplets. As more matter collects, the center of the cloud begins to warm. Not quickly, but steadily. The inward motion of gas creates pressure, and that pressure leads to heat. And at the very center, something begins to take shape. A young star, not yet fully formed, but already beginning to glow faintly. Around this forming star, the rest of the cloud does not fall straight inward. Instead, it begins to rotate, very slowly at first, then a little faster as the cloud contracts, and as it spins, it flattens. What was once a wide, three-dimensional cloud becomes a broad, thin disk, a gently spinning structure of gas and dust circling the newborn star at its center. You might imagine it like a slow whirlpool, not made of water, but of fine particles drifting in a wide, quiet rotation. Within this disk, something subtle begins to happen. Tiny grains of dust, microscopic at first, begin to collide. At first, these collisions are gentle. The particles touch, stick, and move on together. Over time, small clusters form, then larger ones, and gradually these clusters begin to grow. It's a process that takes time, a great deal of time, but it is persistent. Each collision adds a little more mass. Each interaction increases the chance of further growth, and slowly, almost invisibly, these small grains become pebbles, then rocks, then larger bodies. You might think of it like snow gathering. A single snowflake lands quietly, then another and another. Over time, a thin layer forms, then a thicker one, and eventually what was once scattered becomes continuous, solid, shaped. In the disk around a young star, a similar process unfolds. These growing bodies begin to influence their surroundings. Their gravity, small at first but increasing, draws in nearby material. They become centers of accumulation, gathering more and more mass as they move through the disk. And as they grow, their interactions become more dynamic. Some collide and merge, forming larger structures. Others scatter each other, changing paths, redistributing material across the disk. It is not a perfectly orderly process, but it is not chaotic either. It is a kind of guided emergence, shaped by simple rules, repeated over and over again. Eventually, some of these growing bodies become large enough to be considered the early forms of planets. They are not yet the worlds we recognize today. Their surfaces are still forming, their interiors are still hot, their environments are still evolving, but the foundation is there. The disk that once surrounded the young star begins to thin out. Much of its material has been gathered into these growing bodies. What remains is gradually cleared away, some falling into the star, some drifting outward into space. And what is left behind is a system, a star at the centre, and around it a collection of worlds, each following its own path, shaped by its distance, its composition, and its history. Some of these worlds remain small and rocky, others grow large, gathering thick layers of gas around them. Some settle into stable orbits, others are scattered, ejected, or drawn inward. But over time, the system begins to stabilize. Paths become more predictable, interactions become less frequent, and the young star, now fully formed, begins to shine steadily. This process has happened many times across the universe. Stars forming, disks emerging, planets taking shape, and in one particular instance, in one quiet region of a spiral galaxy, this process led to something very familiar, our own solar system. At its centre, the Sun, a star formed from the collapse of a cloud, much like the one we've been imagining, and around it, a set of planets that formed from the surrounding disk. The inner planets, small, rocky and dense, formed closer to the Sun. Where temperatures were higher and lighter, materials could not easily remain. Further out, where it was cooler, larger planets formed, able to gather thick layers of gas and grow to enormous sizes. And among the inner planets, one world began to take on a particularly interesting set of characteristics. A world with just the right balance of materials, just the right distance from its star, just the right conditions for something more to emerge. But even then, it was not yet stable. Its surface was still changing. Its environment was still developing. And one more event, one more interaction, would play a crucial role in shaping its future. An encounter that would leave behind a companion, a quiet partner in the sky, that would help stabilize everything that followed. And as we move gently toward that moment, we begin to see how even a single event can shape the long-term balance of an entire world. As the young world begins to take shape, still warm, still changing, there is a moment in its early history that feels both dramatic and strangely delicate in its consequences, a moment that does not last long, but echoes across billions of years. In those early stages, the inner solar system was not yet calm. There were many forming bodies, moving along paths that were still settling, occasionally crossing, occasionally coming close. And in that environment, encounters were not uncommon. One such encounter, long ago, involved the early Earth, and another large body, roughly the size of a small planet. This object is often referred to as Theia, though the name is simply a way for us to speak about something we can no longer observe directly. What matters is not the name, but the event. At some point, these two bodies came into contact, not in a sudden, explosive way as we might imagine from everyday collisions, but in a vast, slow-motion interaction shaped by gravity, momentum, and immense scales of energy. The surfaces of both bodies were already hot, partially molten, and when they met, material was displaced, lifted outward, stretched into space, forming a cloud of debris around the Earth. It was not a clean break. It was more like a reshaping, a transformation of what already existed into something new. That cloud of material did not simply drift away. It remained in orbit, circling the Earth, gradually spreading into a wide ring. And over time, Just as in the disk around a young star, the particles within that ring began to gather. Small fragments came together, then larger ones. And slowly, through the same gentle process of accumulation we've seen before, a new body began to form, the Moon. At first, it would have appeared much larger in the sky than it does today, closer to the Earth, moving across the horizon more quickly. Its presence would have been unmistakable, bright, steady, and constant. But beyond how it looked, what mattered most was what it did. Because the Earth, in its early state, was not perfectly stable. Its rotation, how it spins on its axis, could have varied more dramatically over time. Without a stabilizing influence, that tilt might have shifted significantly, leading to more extreme changes in climate. The Moon, through its gravitational connection with the Earth, acts as a kind of quiet anchor, not by holding the Earth in place, but by gently guiding its motion, keeping its tilt within a relatively narrow range. You might imagine it like a spinning top. On its own, a spinning top can wobble unpredictably, especially if disturbed. But with the right balance, that wobble becomes steady, controlled, almost graceful. The Earth, with the Moon beside it, spins in a similar way, its motion stabilized, its orientation kept within limits that allow for long-term consistency. And this consistency matters, because the angle at which the Earth tilts determines how sunlight is distributed across its surface. It shapes the pattern of seasons, the flow of energy from equator to poles, the long-term stability of climate. Without that stability, the environment might change too drastically over time for complex systems to persist. The Moon also plays another role, one that is perhaps more familiar. It influences the oceans. Through its gravitational pull, it creates tides, the slow rising and falling of sea levels that occur each day. These movements are not sudden or violent. They're rhythmic, predictable, like a gentle breathing of the planet. Water shifts, moves, circulates. And over time, this motion contributes to mixing, bringing nutrients from deeper waters upward, redistributing heat, supporting systems that rely on steady cycles. In the earlier stages of Earth's history, these tidal forces may have been even stronger, given how much closer the Moon was. The interaction between land, water, and these tidal movements could have created environments where complex chemistry was more likely to occur, places where water flowed in and out, concentrating and dispersing materials, allowing reactions to take place in repeating cycles. It is a subtle influence, but a meaningful one. The Moon does not create life, but it helps shape the conditions in which life can begin and continue. Over time, the distance between the Earth and the Moon has slowly increased. The Moon drifts away at a very small rate, almost imperceptible on human timescales, and yet its stabilizing influence remains. It continues to guide the Earth's motion, to shape the tides, to provide a steady presence in the sky. And there is something quietly comforting in that such a large, silent companion has been there for so long, influencing the rhythms of the planet in ways that are easy to overlook, but deeply important. If we look across the solar system, we begin to notice something else. Not every planet has a moon like ours. Some have many small moons, some have none at all. And the presence, size, and distance of these moons can influence how those planets behave, how they rotate, how stable they are, how their environments evolve. In that sense, the Earth-Moon relationship is not just a detail. It is part of what makes this particular world what it is. A world with relatively stable conditions over long periods of time. A world where cycles repeat, where patterns persist, where change happens, but not so rapidly that everything is constantly disrupted. And as we begin to take all of this in, the formation of the planet, the presence of the Moon, the gradual settling of motion and balance, we move closer to something that feels more familiar, a world not just forming, but functioning, a system where energy flows, where air moves, where oceans circulate, a place where the gentle light of a nearby star begins to interact with a stable surface. And as we step into that next stage, we begin to see the Earth not just as a planet, but as something more dynamic, a place where energy is constantly moving, shaping everything it touches, a quiet, continuous exchange that will set the stage for everything that follows. As the Earth settles into its place, orbiting its star, turning steadily on its axis, accompanied by the quiet presence of the Moon, something begins to emerge that feels almost familiar. Not just a planet, but a system, a place where movement is constant, yet rarely abrupt, where change happens, but in ways that are often smooth, gradual, and interconnected. At the centre of this system is a simple, continuous source of energy, the Sun. From a distance, it appears as a steady point of light in the sky, but what it provides is far more than illumination. It delivers a constant flow of energy to the Earth, energy that arrives gently, spread across the surface, varying with time, angle, and location. You might think of it like a soft, ongoing stream, not overwhelming but persistent. This incoming energy does not stay in one place. It is absorbed by the surface, reflected back into space, and redistributed across the planet through the movement of air and water. And it is in this redistribution that the Earth begins to behave like a living system, not alive in itself, but dynamic, responsive, connected. Imagine sunlight reaching the equator, where it arrives more directly. The surface warms, air near the ground heats up and begins to rise. As it rises, cooler air moves in to take its place. This creates a slow circulation, an ongoing movement that transports heat away from warmer regions toward cooler ones. You don't need to picture complex patterns. It's enough to imagine warm air rising, cool air settling, a gentle exchange that never quite stops. The oceans play a similar role. Water absorbs heat more slowly than land, but it also holds onto that heat for longer. Ocean currents carry warm water away from the equator toward higher latitudes, and cooler water flows back in return. These movements are not random. They form patterns, broad, slow currents that move like rivers within the ocean, distributing heat across vast distances. You might imagine it like a slow circulation within a cup of tea, heat entering in one place, spreading, evening out, creating balance over time. Together, the atmosphere and the oceans form a kind of climate system, a network of flows and exchanges. Energy arrives from the sun. Some of it is reflected away, some of it is absorbed, and the rest is carried, redistributed, and gradually released back into space. This balance between incoming and outgoing energy is what allows the Earth to maintain relatively stable temperatures over long periods. Not perfectly constant, but within a range that allows liquid water to exist. And that in itself is something quite special. Because while water is common in the universe, having it in a liquid form on a planetary surface requires a delicate balance. Too much heat and water becomes vapor. Too little, and it freezes. The Earth exists in a narrow range where water can flow, pool, evaporate, and return again. A continuous cycle that shapes landscapes, supports chemistry, and creates environments where complexity can grow. The atmosphere plays an important role here as well. It acts like a gentle layer surrounding the planet, allowing sunlight to pass through while retaining some of the heat that would otherwise escape too quickly. You can think of it like a thin blanket, not thick enough to trap everything, but enough to keep the temperature from dropping too sharply when the sun is not shining. This effect is subtle, but essential. Without it, the Earth would be much colder, and yet, like everything else in this system, it is part of a balance. Too much heat retained, and the planet could become too warm. Too little, and it could become too cold. What we observe on Earth is a kind of ongoing adjustment, a dynamic equilibrium where different parts of the system respond to one another. If one region warms, currents shift. If conditions change, flows adapt. It is not controlled, it is not directed, but it is responsive. And over time, this responsiveness allows the system to remain within a range that supports stability. There is also another quiet feature that helps protect this balance. The Earth has a magnetic field, a kind of invisible envelope generated deep within its interior. This field extends outward into space, interacting with particles that stream from the sun. These particles, often called the solar wind, carry energy that could, over time, strip away parts of the atmosphere. But the magnetic field gently deflects much of this flow, guiding it around the planet rather than allowing it to directly erode the atmosphere. You might imagine it like a stream of wind flowing around a smooth stone. The stone does not stop the wind, but it changes how the wind moves, and in doing so, it protects what lies beneath. This protection is not absolute. Some particles do reach the upper atmosphere, creating phenomena like the soft glow of auroras near the poles. But overall, the presence of this magnetic field helps preserve the atmosphere over long timescales, and with that atmosphere preserved, the climate system continues, the oceans continue to circulate, the surface continues to interact with incoming sunlight, and the conditions that allow for complexity remain. When we look at other worlds in our solar system, we begin to see how delicate this balance is. Some planets are too close to the sun, where temperatures rise too high. Others are too far away, where heat is too limited. Some lack a strong magnetic field, allowing their atmospheres to thin over time. Others have atmospheres that trap too much heat, creating environments that are difficult for stable, liquid water to exist. The Earth, in contrast, sits within a range that allows for moderation. Not perfect, not unchanging, but stable enough, over long periods, for something more to emerge, and that something more does not appear all at once. It begins quietly, with simple chemical processes, with interactions between water, air, and the surface, with cycles that repeat, slowly building complexity, and eventually, with life. But before we move into that next stage, it is worth pausing here for just a moment, to notice how many layers of balance have come together. A star providing steady energy, a planet at the right distance, a moon stabilizing motion, an atmosphere moderating temperature, oceans redistributing heat, a magnetic field offering protection. Each element on its own is simple, but together they create a system that is capable of something extraordinary, a system that does not just exist, but supports, sustains, and quietly prepares the stage for what comes next. As we rest for a moment within this gently balanced world, a planet where light flows, air moves, and oceans circulate, something else begins to come into focus. Not something large, not something immediately visible, but something quietly present, everywhere. Life, not in its complex forms, not yet in forests, animals, or anything we would easily recognize, but in its simplest expressions. Tiny, almost invisible organisms, drifting, floating, living at the edge of what we can see. And among these early forms of life, there is one group that plays a particularly important role. Small organisms that live in the water, often near the surface, where light from the sun can still reach them. They are simple, but their influence is immense. You might imagine them as a thin, almost invisible layer across the oceans, countless tiny forms, each one interacting with light, water, and the surrounding environment. And what they do is surprisingly gentle. They take in carbon dioxide from the air and water, and using energy from sunlight, they transform it. In the process, they release oxygen, not as a dramatic event, not as something sudden, but as a continuous, quiet exchange, a slow release, happening everywhere at once. Over time, this process begins to change the atmosphere itself. In the early stages of Earth's history, oxygen was not abundant in the air. The atmosphere was very different from what we breathe today. But as these tiny organisms continued their work, day after day, year after year, over immense spans of time, the amount of oxygen gradually increased. It did not happen quickly. It was a slow transformation, like a room that is gradually filled with fresh air not all at once, but through a steady, continuous flow. And as oxygen levels rose, new possibilities began to emerge. Chemical reactions that were once rare became more common. Energy could be used in new ways. More complex forms of life could begin to develop, all because of the quiet activity of organisms too small to see without assistance. There is something almost humbling in that idea, that the composition of the air we breathe is shaped not by large dramatic forces, but by countless small interactions, repeated over and over again. Even today, these microscopic organisms continue to play a central role. In the oceans, tiny plant-like forms, often referred to as phytoplankton, float near the surface, where sunlight is available. They are carried by currents, rising and falling gently with the movement of the water. And as they drift, they continue this same process, taking in carbon dioxide, releasing oxygen, supporting not only themselves but the entire chain of life that depends on them. You might think of them as the foundation of a vast interconnected system, not visible in the way larger organisms are, but essential nonetheless. Without them, the balance of gases in the atmosphere would be very different. The flow of energy through ecosystems would change, and the conditions that support life as we know it would begin to shift. There is also a quiet rhythm to their existence. They grow when conditions are favourable, when there is enough light, enough nutrients, enough stability, and they decline when conditions change. But across the planet, these patterns balance out. In one region, populations increase. In another, they decrease. And over time, the overall system remains relatively stable. It is not fixed, it fluctuates, but it does so within limits that allow the broader system to continue. And this brings us to an important idea. Life does not simply exist within the environment. It interacts with it. It shapes it. It participates in the ongoing balance of the planet. The air, the water, the surface, all are part of a network of exchanges. Carbon moves from the atmosphere into living organisms. Oxygen moves from organisms into the air. Nutrients cycle through different forms, different locations, different states. Nothing remains static. Everything flows. And through this flow, a kind of equilibrium emerges. Not perfect, not unchanging, but stable enough to persist. It's a bit like a quiet conversation. Many voices, each contributing in small ways, adjusting to one another, creating a shared outcome that no single participant controls. And within that conversation, life and environment become deeply intertwined. The Earth is no longer just a physical system of air and water. It becomes something more integrated, a place where living processes and physical processes are connected, each influencing the other. Over time, this connection becomes stronger, more complex, more layered, but at its foundation, it begins with something very simple: tiny organisms interacting with light, transforming one kind of molecule into another, changing the composition of the air. One small exchange at a time. And as we begin to follow these exchanges more closely, we find that they are part of a larger cycle, a continuous movement of elements through different parts of the Earth, from the air to the ocean to living things to the ground and back again. A slow, circular journey that connects everything together, and it is within that journey that the long-term stability of the planet is maintained. If you follow that quiet exchange a little further, the movement of air, the drifting of tiny organisms, the slow changes in the atmosphere, you begin to notice a pattern that feels almost circular. Nothing stays in one place for very long. The same elements move, again and again, through different parts of the Earth. And among these elements, one plays a particularly important role: carbon. It is not rare. It is not especially dramatic on its own. And yet, it is central to the structure of life, to the behavior of the atmosphere, and to the long-term balance of the planet. To understand its role, it helps to think of carbon not as something fixed, but as something that travels, a quiet traveller moving through air, water, living things, and even rock, over timescales that range from moments to millions of years. Let's begin with the air. Carbon exists in the atmosphere in the form of a gas, carbon dioxide. It drifts invisibly, mixing with the air, carried by winds across the planet. Some of it dissolves into the surface of the ocean, where it becomes part of the water itself. Some of it is taken in by living organisms, especially those tiny drifting forms we spoke about earlier, which use sunlight to transform it into something else. In doing so, they incorporate carbon into their own structure. It becomes part of their bodies. And when those organisms are consumed by others, or when they eventually die, that carbon moves again. It sinks into the ocean, or settles onto the surface of the land, or becomes part of the soil. You might imagine it like a leaf falling from a tree. At first it is part of something living, then it drifts downward, becoming part of the ground, slowly breaking down, returning its material to the environment. Carbon follows a similar path, but on a much broader scale. In the oceans, some of this carbon becomes part of tiny shells or skeletal structures formed by microscopic organisms. When these organisms die, their remains sink to the ocean floor, gradually building up layers over time. These layers, compressed and transformed over long periods, can become part of the solid Earth, locked within rock. At this stage, the carbon is no longer moving quickly. It becomes part of a slower cycle, one that unfolds over millions of years. Deep within the Earth, processes continue. Heat and pressure reshape the material. Plates of the Earth's surface shift slowly, carrying rock from one place to another, sometimes pushing it downward into the interior. And eventually, in certain regions, this material can return to the surface. Not gently this time, but through volcanic activity. When a volcano releases gas, it carries carbon back into the atmosphere, completing a long journey that may have taken tens of millions of years. From air to ocean to life to rock and back to air again. It is a cycle, a slow, continuous loop that connects the different parts of the Earth into a single system. And what makes this cycle so important is not just that it moves carbon, but that it helps regulate the balance of the planet. When more carbon is present in the atmosphere, it can influence how much heat is retained. When less is present, that balance shifts. But because carbon is constantly moving, being absorbed, stored, released, and redistributed, the system tends to adjust over time. Not perfectly, not instantly, but gradually. If the atmosphere contains more carbon, more of it can be taken up by the oceans or by living organisms. If less is present, processes that release carbon can become more significant. It is a kind of feedback, a quiet adjustment, happening across many different parts of the system at once, You might think of it like water flowing through a landscape. If more water enters a region, it spreads, fills low areas, moves along channels. If less water is present, those flows diminish. But the system as a whole adapts, redistributing what is available. Carbon behaves in a similar way. It does not remain static. It flows. And in flowing, it helps maintain a kind of balance. There is also something else to notice. The timescales involved in this cycle are very different. Some parts happen quickly, a plant taking in carbon from the air, releasing oxygen, all within moments or hours. Other parts happen slowly, carbon being locked into rock, then returning through volcanic processes over millions of years. And yet these fast and slow processes are connected. They form a single system, with layers of movement occurring at different speeds. This layering is part of what makes the Earth so stable over long periods. Short-term changes can be absorbed, adjusted, balanced by slower processes that act over longer timescales. It is not a system that resists change entirely, but it is one that can moderate it, and within that moderation, conditions remain within a range that supports ongoing complexity, including life. There is something quietly elegant in this, that a simple element moving through different forms and locations can contribute to the stability of an entire planet, not by design, not by intention, but through the accumulation of many small processes working together over time. And yet, this balance is not unbreakable. It can be shifted, it can be disrupted if changes occur more quickly than the system can adjust. And when that happens, the consequences can unfold across the entire planet. But even then, the system does not collapse instantly. It responds, it shifts, it moves toward a new balance, though that balance may be very different from what came before. As we move forward, we'll look at one such moment, a time when the Earth's balance was pushed, when conditions changed more rapidly, and the system had to respond, not in chaos, but in a quieter, more gradual transformation. A reminder that even in a system as stable as this, change is always possible, and sometimes it comes from deep beneath the surface. As we sit with that image of a slow, continuous cycle, carbon moving quietly through air, water, life and rock, it can begin to feel as though the Earth is gently self-correcting, a system that adjusts, that balances, that absorbs change and redistributes it over time, and for long periods, it does. But every so often, something deeper shifts, not at the surface, not in the air or the oceans, but far below, where the Earth is still warm, still active, still slowly moving from within. Beneath the surface, the Earth is not still. The outer layer, the ground we walk on, is made up of large sections, slowly drifting, sliding past one another, sometimes pulling apart, sometimes pressing together. These movements are incredibly slow, so slow that we rarely notice them in our daily lives. But over long periods of time, they reshape the planet, and in certain regions these movements allow heat from deep within the Earth to rise toward the surface. Not always in small, localized ways like ordinary volcanoes, but sometimes in much larger, more expansive events that do not form a single mountain or a narrow vent, but affect entire regions. These are often referred to as supervolcanoes, but rather than imagining them as towering peaks, it may help to think of them as vast underground systems, large reservoirs of molten material, slowly building pressure beneath the surface. For long periods, nothing seems to happen. The surface above may appear calm, unchanged, but below, conditions are evolving, heat accumulates, material shifts, pressure increases, and eventually, that pressure finds a way to release. When it does, the release is not always sudden in the way we might expect. It unfolds over time, but on a scale large enough to influence the entire planet. Material rises from below, spreading across the surface and into the atmosphere. Fine particles, ash, gases are carried upward, then outward, drifting across continents and oceans. From a distance, it might appear as a soft veil, a thin layer spreading through the upper atmosphere. And as this layer forms, something subtle begins to change. Sunlight, which normally reaches the surface with relative ease, becomes partially scattered. Not blocked entirely, but diffused, reduced. The energy reaching the surface begins to decrease. Temperatures begin to shift, not instantly, but gradually. The planet cools. You might imagine it like a room where the light has been dimmed. The warmth remains for a while, but over time it begins to fade. The air grows cooler. The patterns of movement begin to change. Winds shift, water circulation adjusts, and living systems respond. Not all at once, but in stages. Some environments become less favourable. Some populations decline. Others adapt, shift, or move. It is not a sudden disappearance of life. It is a quiet contraction, a narrowing of conditions, a period where the balance we spoke of earlier is pushed in a new direction. One example of such an event occurred long ago in a region that is now part of Southeast Asia. This event, often referred to as the Toba eruption, released an immense amount of material into the atmosphere. But rather than focusing on the scale of the eruption itself, it may be more helpful to think about its effects. For a time, the Earth experienced cooler conditions. Sunlight reaching the surface was reduced, ecosystems adjusted, life continued, but within a more limited range. And over time, as the particles in the atmosphere settled, as the system responded, conditions began to shift once more. The sunlight returned, temperatures rose, the cycles resumed, the system once again moved toward a new balance. There is something important to notice here. Even when the balance is disturbed, the Earth does not fall into disorder. It changes, it adapts, it finds a new state. But that new state may not be identical to what came before, and the transition, while gradual, can shape the course of life for long periods. It reminds us that stability is not the absence of change, it is the presence of processes that allow change to be absorbed, redistributed, and eventually integrated. The Earth's systems, the atmosphere, the oceans, the land, and the life within them are all connected. When one part shifts, the others respond, sometimes gently, sometimes more noticeably. But always within the framework of those same underlying processes: energy flowing, matter cycling, balance adjusting. And perhaps there is something quietly reassuring in that even when the surface appears calm, there are deeper processes at work, and even when those deeper processes lead to change, the system as a whole continues, it evolves, it persists, and over long stretches of time, it creates new conditions, new environments, new possibilities. As we move forward from this moment, from this reminder that balance can shift, we begin to widen our view once more, beyond this single planet, beyond its cycles and adjustments, outward to other worlds, other systems, other stars, and we begin to ask a simple question. If the conditions that allow for balance and life have emerged here, could they emerge elsewhere? And if so, how would we recognize them? Not by seeing them directly, but by noticing the subtle signs, the small movements, the quiet patterns, that reveal the presence of something beyond what we can immediately see. As we gently lift our gaze once more, from the surface of the Earth, from its oceans, its air, its slow and steady cycles, we return to a wider view, outward, beyond this one world, back into the quiet expanse where stars drift, where galaxies stretch across space like distant islands, and where countless other systems continue their own slow, unfolding stories. And with that wider view, a question begins to form. If the conditions that allowed life to emerge here were shaped by a series of processes that are not unique, then could something similar be happening elsewhere? Not in exactly the same way, not with the same details, but with the same quiet principles. A star forming, a disk of material gathering, worlds taking shape, energy flowing, balance emerging, and somewhere within that balance, the possibility of life. To explore this question, we begin not by travelling to those distant worlds, but by observing them from afar, because the distances are vast, so vast that even the nearest stars are separated from us by spaces that take years for light to cross. And so, we rely on subtle signs, small changes, gentle shifts in light that reveal the presence of something we cannot directly see. One method involves watching a star very carefully, noticing if it moves ever so slightly over time, not in a large visible way, but with a small, almost imperceptible motion, a gentle wobble. This motion can occur when a planet orbits the star. The planet, though much smaller, still has mass, and as it moves, it creates a small pull on the star itself. The two bodies move together, each influencing the other. From a distance, this causes the star to shift slightly, first in one direction, then another, in a slow, repeating pattern. By observing this motion over time, we can infer the presence of a planet. We do not see the planet directly, but we see its effect. It is a quiet kind of detection, a way of knowing something is there, by how it influences what we can observe. Another method is even more subtle. If a planet passes between its star and our line of sight, it can block a tiny fraction of the star's light. Not enough to dim the star noticeably to the eye, but enough to be measured with careful instruments. The star's brightness dips slightly, then returns, and this pattern repeats at regular intervals, like a soft pulse. From this repeating dimming, we can determine not only that a planet is present, but also how long it takes to orbit its star, and even something about its size. These methods, watching for gentle motions, noticing slight changes in light, have allowed us to discover thousands of planets beyond our solar system. Some are large, orbiting very close to their stars, others are smaller, more distant, and among them, a few lie within a region often described as the habitable zone. This is not a special boundary in space. It is simply a range of distances from a star where conditions might allow liquid water to exist on a planet's surface. Not too close, where temperatures would be too high. Not too far, where everything would remain frozen, but somewhere in between. A region where energy from the star arrives in a way that could support balance. But even here, it is important to be gentle with our expectations, because being in this region does not guarantee anything. A planet may be at the right distance and still lack an atmosphere, or it may have an atmosphere that traps too much heat, or too little. It may not have a magnetic field to protect it, or it may lack the internal activity needed to support long-term cycles. As we've seen with Earth, habitability is not determined by a single factor. It is the result of many conditions working together. Distance from the star, atmospheric composition, magnetic protection, geological activity, the presence of water, and the ability to keep it stable over time. Each of these contributes quietly to the overall balance. And while water itself appears to be common, found in comets, in icy moons, in distant regions of space, the combination of conditions that allow water to remain liquid on a surface over long periods is far more delicate. It is not impossible, but it is not guaranteed. And so, as we continue to observe these distant worlds, we begin to understand something subtle, that the universe may be filled with planets, but worlds like Earth may require a rare alignment of factors, not unique, but uncommon. And this realization does not make the universe feel smaller. If anything, it makes it feel more meaningful, because it reminds us that what we experience here, this balance of light, air, water, and life, is the result of a long chain of processes, each one building upon the last, a chain that stretches back to the earliest moments of the universe, to the formation of stars, to the creation of elements, to the shaping of galaxies, to the quiet influence of black holes, all the way to this moment where we sit, aware, able to reflect on it all. And as we let that thought settle, another possibility begins to appear, one that extends even beyond the idea of distant planets. Some theories suggest that the universe itself may be far larger than what we can observe, that beyond the regions we can see, there may be other vast areas, perhaps with different conditions, different histories, even different outcomes. It is a speculative idea, not something we can confirm directly, but it arises naturally from the way the universe appears to expand and from the patterns we observe at the larger scales. And while we do not need to resolve that question here, it offers a quiet perspective that the universe may not be a single, isolated story, but part of something even broader, a wider landscape of possibilities, and within that landscape, our own existence becomes both small and deeply connected. Because everything we have followed, from the earliest expansion of space to the formation of stars to the cycles of matter on Earth, has led to a moment like this, a moment of awareness, of reflection, of quiet curiosity, and perhaps that is one of the most gentle conclusions we can reach, that the universe, in all its vastness and complexity, has given rise to places where it can be observed and wondered about, not everywhere, but somewhere, here and maybe elsewhere. And so, as we come to the end of this journey, you might find your thoughts slowing, drifting, settling into that same quiet rhythm we've followed throughout. A rhythm of unfolding, of gentle change, of connections that stretch across time and space. And whether your eyes are still open or already beginning to close, the universe continues quietly all around you.